Hi, so my name is Elie, and today I will be presenting our work titled Volumetric Inverse Rendering via Neural Radiative Transfer. So participating media are everywhere, and they include things such as clouds in the sky, fog, smoke, underwater scenes, and even our skin exhibits volumetric properties. And so one way we can imagine this participating media is as a region of space being filled up with a lot of tiny particles. And as light travels through this space, it will undergo a lot of interactions with these particles. Now, how these interactions happen, or the rate at which these interactions occur, is determined by what are known as the optical properties of the medium. The first of which is the absorption, giving us the ability of the medium to absorb light. The scattering, which is subdivided in outscattering and inscattering, being the ability of the medium to either redirect light in other direction or aggregate lights coming from other directions. The emission being the ability of the medium to generate its own light. And finally, the phase function, which in this case, we will use the Heine-Greenstein function, which is parameterized using an anisotropy parameter G, depending on whose value the scattering can either be isotropic for 0, forward scattering for positive values, and backward for negative values. And so, assuming we are given these optical properties, we can use the radiative transfer equation as the physical model for light transport in participating medium. And this equation essentially describes how radiance changes as it travels within a participating medium, change which is mainly due to loss due to extinction and gain due to emission and inscattering. In practice, performing volumetric light transport simulation, however, is done using the volumetric rendering equation, which is the integral form of the radiative transfer equation. And what this equation tells us or gives us is radiance at a position in a direction omega by aggregating contributions along a ray. And so our goal in this work is to solve the inverse problem where we are given a set of observations depicting a participating medium, and we would like to inverse this rendering process so as to obtain the optical properties that explain our observations. Now, as we probably all know, inverting the volumetric rendering equation is very hard. And one of the reasons this is so hard is because the light arriving at a viewer is the result of a very complex aggregation within this space, a process which is highly non-local, can be expansive to perform, and when performing the inverse problem can result in high variance in the gradients. As a result, existing methods typically rely on simplifications, the first of which is to simply assume that the model that we use is an emission absorption model. This is now very common using methods such as NERF and other work that follow up on this one. The only downside is, however, that this tends to completely discard scattering, and as a result, the optical properties that we obtain are typically non-relatable in a physically based rendering way. Now, there's another series of work that tends to approximate the scattering, but by only considering direct lighting. This, however, typically does not support the full scale of type of global illuminations one can consider. And these include methods such as relightable nerves and other relightable methods following from that. And so putting everything into perspective, on the left side, we have the full inverse volumetric rendering, which typically relies on path sampling. It is accurate, it is global, it is full. However, when using these methods, there's typically a price to pay in terms of like specialized renderer, high gradient variance, and all this. While on the other side, we have these methods that typically rely on simplifications. They are practical, they are good, everybody loves them, but typically they tend to make strong simplifications on the physics. And so our goal in this work is to kind of reconcile the global nature, the completeness, the physical completeness of the methods on the left with the practicalities of method on the right. And to achieve this, rather than performing the simulation explicitly as would have been done via path sampling, we would like to embed this physics implicitly within our optimization framework. So to achieve this goal, we introduce a method to recover physically meaningful optical properties of participating media without using the full light transport simulation and without reverting to these simplifications. So we assume we are given a set of multi-view images. We represent the scene's optical properties and scene light field using two implicit neural representations, and then proceed to optimize them jointly using a set of physical and data constraints. As a result, the optical properties that result from this system are physically meaningful, and as a result can be used for downstream applications such as novel view synthesis and relighting with global illuminations. Moreover, because our framework is 100% neural, it can also be extended to other applications such as generative modeling. So our pipeline is as follows. We are given data in the form of multi-view images and also known illumination. We represent the scene's optical properties and scene light field using a neural medium field and neural light field, taking in as input spatial and spatial angular coordinate respectively, and outputting optical properties and scene radiance. And then we optimize this framework using a set of objectives, the first of which is the radiative transfer equation. We add our observation via an observation constraint. We include the illumination as a boundary condition. And finally, we also add a non-local constraint in the form of the volumetric rendering equation. So starting off with the radiative transfer equation, one thing to note here is that the L subdata, which is the radiance, and our optical properties are now parameterized using neural fields. So we can do some massage here by moving everything to the left side, resulting in the residual of this equation, and then we can simply enforce this residual as an objective to be optimized. In practice, the way we minimize this objective is by simply sampling a bunch of points in our computational domain and then minimizing this physical equation for all these points. So this is a data-independent term. The second objective are observation constraint, and the main goal of this constraint is to make sure that the light exiting the medium is consistent with our observation. And so for illustration purpose here, for a given camera located at O sub k and a direction of propagation, we simply minimize the mismatch term between our observation for an image I sub k at a pixel q and the value sampled from our neural light field at the corresponding position and direction. The goal of enforcing this boundary condition is to incorporate the non-illumination within this optimization. Prior to doing this, we first classify our computational domain into inside and boundary, and we assume also we are able to compute a normal vector for our boundary. And then we sample a bunch of points with directions on this boundary such that these sampled points and direction are adhering to the inflow boundary condition. Yes. And then we simply minimize the discrepancy or mismatch term between the known lighting and the value of our neural light field sampled at corresponding position and directions. So at this point, if we are to look at the optical properties recovered from our method, we can see that they are significantly lower frequency compared to the reference. And the main reason this occurs is due to an issue of spectral bias inherent to neural network, but not in the sense that you typically know it. So in this case, what we are trying to do is we are trying to solve an inverse problem by using physical constraints, and all these physical constraints are enforced in a pointwise fashion. And so to mitigate this issue, we introduce an additional non-local constraint in the form of the volumetric rendering equation. And in contrast to these local constraints that we have, this non-local term allows us to perform integration throughout the entire, on the entire camera array. And as a result, provides us with coupling between each pixel observation and the full light transport path within the volume. So this is probably the easiest. typical stuff. We sample a ray, cast it within the volume, sample along this ray, and then for each of these points, we simply aggregate the in-scattering. But one thing to note here, if you're familiar with this, you would probably imagine that for each of these points on the ray, we would then cast children ray, who will have children rays, and so on until we have this explosion of rays. But this is not the case, because by simply enforcing the previous loss that I talked about, which is the radiative transfer equation, our entire formulation already enforces global illumination. And as a result, to simply sample this in scattering term, we just have to sample our neural light field at other light directions on the sphere without having to cast additional rays. And the way this is done is very simple. It's simply a mismatch term between our observations and the result of this integration. Now, when we observe the optical properties that we are able to recover, we can see that we are now able to recover higher frequencies, and our results are much closer to the ground truth. Now, so far, our pipeline is as follows, and it's scene-specific, but it doesn't have to remain like that. So one thing that we can do is extend this framework to a generative modeling setup, where we are now dealing with multiple scenes, each being tied to an optimizable latent vector, such that at evaluation time, we can sample from the same distribution of these latent vectors, which can allow us to generate novel, physically meaningful, and physically plausible participating media. Now, let's look at some results, and I will present results as follows. On the left side, I will show slices of optical properties that we can recover. And on the right side, I will show how these optical properties are used for the downstream task of relighting. So our method is on the third row, in case your eyes get lost. And you can observe that the optical properties that our method recovers, namely the absorption scattering and their addition, which is the extinction, is very competitive with the first row, which is the differential ratio tracking, and also when compared to the reference, we see that it is quite close. We can also see on the right side, when we take these optical properties and use them for the downstream task of relighting, we can again see that our results are much closer to differential ratio tracking, which is the state of the art, and also much closer to the reference. So we can, again, observe the same for a different scene here. And now, looking at something that is a little bit more interactive. So in this case, we are performing a relighting task, and we have a rotating environment map, and we are comparing our method in the middle to the left, which is differential ratio tracking based on a path sampling Monte Carlo method. And on the right side, we have the reference. And as we can, again, observe in this case here, the results that are recovered from our method, which are shown here rendered, are much closer to the reference and very competitive with the state of the art. Now, in terms of generative capabilities, here I'm going to show samples, 3 samples from our generative model. And in this case, these 3 samples are showed under the same illumination that was used during training. We can again re-render them under a novel illumination, and we can see that things change, highlighting the fact that the optical properties that we recover are actually physically meaningful. So to conclude, we introduce a novel formulation for volumetric inverse rendering, accounting for full global illumination with only minimal reliance on transport-specific simulation. This is made possible by a joint estimation framework where we represent scenes, optical properties, and scene light field using implicit neural representation. And we also experimentally demonstrate the ability of our method to recover scene-specific optical properties, and also how this method can be extended to generative modeling of physically meaningful participating media. So I'll be happy now to take questions, if any.
Thank you for the presentation. It's a cool work. I was wondering, did you get inspiration of physics-informed neural networks?
Yes, it's based on a physics-informed neural network. Yeah.
Okay. Yeah, that's really cool. It's like I think it's the first time I see this application in the computer graphics.
Oh yeah, yeah. I mean, physics-informed neural networks are actually getting tractions now in computer graphics, and within the rendering community, not so much. But if you look at people doing physical simulation, there's already quite a few of them using this type of physics-informed work.
Ah, like the fluid simulation.
Yeah, the like fluid simulation people. Yeah.
Okay. Yeah. Thanks.
Thank you, very elegant work, really liked it. Maybe one question,
Yes.
like if we look at like usual like neural radiance field and stuff like that, like NERF, they're used to acquire more surface-like scenes,
Yes.
like earth surface scenes through like the fact that volumetric is more easily differentiable and stuff like that.
Yeah.
You haven't shown scenes that are that has this property of like being very hard volumes that almost approximate surface. Do you think it will be extendable to cover such stuff and basically be able to do at long last like relatable neural well NERF and maybe Gaussian splatting at some point? Who knows?
Yeah, so just to repeat your question, you are asking whether the method is extendable to hard surfaces.
Yeah, like NERF is.
NERF-like surfaces. Okay, so this is actually a very important question. And from the radiative transfer literature, one thing that we know is that if we increase the extinction to infinity, we get a hard surface. Now, we have tried a few experiments. And what we have observed is essentially that as the extinction becomes extremely large, and that as the surface starts to reach hard level, the performance of our method start to deteriorate. So I could assume that follow-up work, which we could do, is probably, we could come up with a way to make this happen. But in the current state, we see a degradation in performance when we use hard surfaces.
Thank you. Very nice work.
All right, in the interest of time, let's thank the speaker again and move on to the next topic.